Good afternoon, everybody, and welcome to the Computational and Colloquium series. Today I have the pleasure to welcome Professor Paolini, our own. He's an alumni of the CSRC, and he's going to talk about a project that is actually very interesting for carbon sequestration and future things related to CO2 injection.
All right, thank you very much. So title of my talk, Reactive Transport Modeling of Diffusion Front Temperature Variation During Subsurface CO2 Injection. And what you're seeing is a plot of a recent simulation we just ran. And this is a plot showing pH. And so the red area, the red regions are more acidic, the blue regions have higher basicity. And this is a plot of pH contour in the perforation zone where you have a well bore at say 1,500 meters and you're injecting CO2 into the subsurface. And so this is the injection point. So this is a plane orthogonal to the z-axis. And an interesting effect that you can observe just by this contour plot is that you have a highly acidic or a more acidic region developing in front of the effluent. So this blue region is where the bulk of the injectant is. And a phenomenon that we observe is there's a more acidic region that diffuses in front of the bulk. And I'll show you how this region has a little bit lower temperature than the bulk. Something interesting. Okay, so the motivation for this talk is trying to understand or come up with a hypothesis for this short-term side effect that we see when you inject CO2 into the subsurface. You see this low pH front that forms ahead of the bulk. And another phenomenon that we see is in this acidic region, we see a decrease in temperature. So there's a cooling effect. And I wanted to find out what is causing this decrease in temperature within the acidic zone. It's something that people are debating, and I wanted to show through numerical simulation one possible idea that sort of counteracts with what most people think it could be. And in these simulation results I'm going to show you, these are results of a code we've been developing in-house over the past several years. And one of the models I added to this code is called the Helgeson-Kirkham-Flowers model. And this model allows you to compute the temperature effect caused by the interaction of charged electrolytes in an aqueous solution. So the numerical results I'm going to show you and the code I've developed, we configured this code to model an actual classic test that was done by Lawrence Berkeley Labs and UT Austin. And this test, yes, sir.
Do they inject gas or do they inject the solution?
It's gas, but the gas reacts with formation water and it becomes aqueous. So it's supercritical phase CO2, but as soon as it hits the reservoir water, it solvates, and then you have a CO2-rich aqueous phase. Okay, so the simulations I configured are based on an actual test done by LBNL, and this test is known as the Frio brine pilot. And in this test, 1,600 tons, those are metric tons, of CO2 were injected at 3 kilograms a second into the Frio formation, which is in Dayton, Texas. It's a depleted oil reservoir. And the perforation zone was at 1,539 meters, and the injection lasted 10 days. But the total injection time was about 6 days. I'll show you in a plot where they shut off the pump for part of the time. Now, 30 meters away from the injection well, they have another well, which was used for observation. So in this observation well, they dropped in this U formation measurement chamber, and they collect formation water and they measured and then at depth they had pressure transducers, temperature sensor, but then they collected the reservoir water, and then they were able to do solute concentration analysis. So all that data was collected, and I was fortunate enough to get that data from Sue Horvorka, which is the PI on this project. So you can see in this diagram here, the green region is the actual plume that developed over the 10-day period. And the black line, the black contours represent what is predicted to be the CO2 plume. What you're seeing in this green region is CO2 saturation. Okay, so that's where the injectant was. And you can see even over, say, 30 days post-injection, this CO2 plume sort of remains static within the injection region. It didn't migrate beyond this. Okay, the black line represents what's predicted by numerical simulation. You can see the depths that are involved and the perforation interval that was used in the injection. Okay, so like I said, I was fortunate enough to get the actual data. Sue Horvorka at UT Austin shared it with me. And what we have here, what I've plotted for you is the temperature profile, and over 30 days. So the red line is the actual temperature, and what you can see in this plot is, okay, these green boxes I have here are actual injection periods. So in between these green boxes, the pump was turned off. Okay, so I labeled them A, B, C, D, and E. And you can see that in the C region, which is called the breakthrough, it's where the plume broke through or passed through the observation well. You can see what happened on day 2. There was a great drop in temperature, and then a rise in temperature back, and then temperature gradually increased over the next phase period, and it sort of increased and increased and increased. And even at 30 days, we saw from the previous plot how that plume remained in place and didn't migrate so much beyond what you saw. So a question became, I asked Sue Horvorka, what caused this drop in temperature? And she said that she didn't know, and that it could be a result of a sensor malfunction. Yes, sir.
What was the radius of the plume from the wellbore?
The radius, so at 4 days, well, at day 2, it's 30 meters away. So this is the observation well. It broke through, so it reached 30 meters after day 2. Yeah, because this is data from the observation well. Okay, so some questions. So there's some questions. What caused that sudden drop in temperature? And what explains the gradual increase in temperature after the temperature recovered? Now, a lot of people, so I went to several conferences and I showed this data, and people came up with different hypotheses of what could be going on. And what most people thought it is Joule-Thomson cooling, right? So we've experienced Joule-Thomson cooling when you have a sudden release of gas into a low pressure or into a vacuum, you have, and it's an adiabatic expansion, you'll have a decrease in temperature, right? So well, the current theory is at this breakthrough, you have a expansion of the CO2. It happens very quickly, so you can assume adiabatic, right? There's no heat being transferred to the surroundings. So if you're doing PV work on the fluid and enthalpy is constant, you have a decrease in internal energy, and that could explain the decrease in temperature. But there's a couple of problems with that. One is, if you look at 1, corresponding with the decrease in temperature is a sudden increase in pressure. So superimposed on the temperature line, the blue line is the pressure. So in section 1, where you see the sudden drop in temperature, you have a corresponding increase in pressure. So in zone 1, delta T is negative, delta P is positive, right? But then after zone 1 and zone 2, temperature and pressure are both increasing. So delta P, delta T are both positive, right? And then here's this third region is where they shut the pump off. Temperature increased when the pump was off. And then there's a gradual increase in temperature. And this is the mechanical equilibrium being reached in the formation, right? Where there's no injection anymore. So we have these different zones. Now, if you consider Joule-Thomson cooling, one thing you want to look at is the Joule-Thomson coefficient, right? The Joule-Thomson coefficient is partial T partial P at constant enthalpy, right? H is enthalpy. Now, which means that when the Joule-Thomson coefficient is positive, if there's a change in temperature, there has to be a corresponding positive change in pressure. And if there's a decrease in temperature, delta T is negative, there has to be a decrease in pressure. But we saw at that breakthrough that pressure increased and temperature decreased. But then after that breakthrough, yes, temperature and pressure were both positive. Now, if we look at this plot from this 2015 plot, you can see at selected constant temperatures over a range of pressures, the Joule-Thomson coefficient is always positive. And in the other plot, at a specific pressure over a range of temperatures, the Joule-Thomson coefficient is also greater than 0. So how could the corresponding increase in pressure also agree with the corresponding decrease in temperature if it's truly Joule-Thomson cooling? So that's a problem that I'm trying to solve in this work. Okay, now here is a plot of species concentration taken from the sampling at the observation well. And you can see that, so these black dots are actual pH, okay? So at this particular time, so here's time on the x-axis. Okay, injection started on the 4th, and then 2 days later on the 6th, we see a sudden drop in pH. So this is what I claim is this acidic front that hits the observation well first. Then a little bit of time later, and this is a gap right here, we see, if we look at bicarbonate concentration, now bicarbonate is produced when you have a deprotonation of carbonic acid. So the CO2 hits the formation water and forms carbonic acid in solution, right? That's H2CO3. Then then it deprotonates and you get HCO3. So this is the bicarbonate, and the bicarbonate sort of marks where the bulk injectant is. And you can see at this period of time where the green line is, your bicarbonate concentration ramps up. So that's where I claim the bulk has arrived. So first this acidic portion arrives, then a time later the bulk arrives of the injectant, marked by the bicarbonate concentration. Okay, now the question is, how can we simulate this numerically and have an explanation of why this is occurring? Over here on this plot, I plotted predicted separation distance. So on the z-axis is the distance in meters between the predicted difference in meters between the acidic front and then coming the bulk. And this, we predicted through simulation that this distance varies as a function of temperature and your what's called seepage velocity, which is the flux through the porous medium. All right, so that's variable. Okay, now now here's a visualization. This is a slice. So the code is 3D. and I use ParaView to capture a slice. And this is a slice orthogonal to the x-axis. Oh, sorry, to the y-axis. It's a long, so this is a slice orthogonal to the y-axis along this injection. So here's the injection, here's the plume that forms. This results from our code. And this is a slice taken here. And then you can see contours of temperature and pH, okay? So what you're seeing, temperature is the color, and higher temperature is more yellow, colder temperature is more blue, okay? So, and then this is the background temperature of the reservoir, okay? So you can see from computing temperature, there's this region that's a bit colder developing ahead of this region, which is the bulk, okay? The effluent. Now, the lines, the white and black lines are pH. So whiter is more acidic. Whiter is more basic, right? Higher pH. Whiter is more basic. Blacker is more acidic. Now, you can kind of see developing in here, these lines are getting darker. Like here's a darker line. So this is a more acidic region, pH of 2.63. This is a more acidic region that's forming ahead of the bulk, and it's in this colder zone. Now, if we take that same plot and we also plot bicarbonate concentration, I've done that in shades of green. So we can see the thicker contour line from white to green is bicarbonate concentration. So the greener the line, the higher the concentration of bicarbonate. And the thick white line that you see that I have with the arrow indicates where there's a change in bicarbonate concentration different from the initial reservoir bicarbonate concentration. The reservoir water has a certain concentration of bicarbonate. So that thick white line sort of represents where the beginning of the higher bicarbonate concentration is, and that's what we're saying is the bulk effluent. And you can see here, compared to the initial reservoir bicarbonate, this is where the front forms. And look how interesting this is. The bicarbonate front is forming right behind this colder region that develops that's lower pH. Okay, so that corresponds with what we saw from the data. Okay, so we see this in this simulation from our code. We see the same drop in pH before the arrival of a high concentration of bicarbonate at 30 meters in 7 days. Okay, so now how does our code work, or how did we model this? Well, one thing we need to model is solute diffusivity. So diffusivity is a function primarily of temperature. And this is the simple linear model we use. And our code computes solute diffusivity different for each ion. So we don't use a constant diffusion coefficient. Our diffusion coefficient is variable and it's solute specific. And one thing you can see from this plot that I created is that the diffusivity of hydronium ion, right, is a magnitude greater than that of bicarbonate. Okay, so here's hydronium, H+, we'll say, and it's much greater than bicarbonate. And so you can see just by the difference in diffusivity, well, it's a much smaller molecule, that it's going to diffuse at a greater area rate, right? Because diffusion is area per unit time. It's going to diffuse at a much greater area rate than bicarbonate. So when the injection is occurring, you see this acidic front that's diffusing ahead of the advective front is what I'm claiming. And that explains that acidic front. Okay, now what explains what could explain the decrease in temperature? Because the question is, why is temperature decreasing in that acidic zone? If it's not Joule-Thomson cooling, or if it's Joule-Thomson cooling and interaction between charged electrolytes. So to model this, what I did is I used the Born solvation model. And the way this model works is you consider the change in temperature as a result of ion-ion interaction. Okay, so the question is, could the interaction between solutes and the formation water solvent play a contributing factor in the decrease in temperature in that acidic zone? Now, one thing is that each charged ion forms an electric field, okay? And the work done by the electric field is in reorienting dipoles. So if you have a charged ion in water, there's surrounding water, work is done in order to reorient the dipoles so that they align with the charged ion. Okay, and so what you do is you can model a charged ion in a solvent by considering the solvent having an electric field with a given permittivity epsilon. Okay, so permittivity is a measure of the material, in this case the formation water's ability to store energy in the electric field. And it stores energy, it's kind of like a capacitor, it stores energy in this electric field by reorienting the dipoles. It takes work to reorient those dipoles around the charged ions. Okay, now an ion's charge will yield more electric flux in a solvent with low permittivity, and that means that it won't be able to store energy through reorientation of dipoles. Okay, more than if the solvent has high permittivity. So if the solvent has high permittivity, it's going to store more energy through the dipole reorientation, kind of like a capacitor, as I said. So to compute temperature, which is what we want to do, we need to compute the change in energy of solvation, which is the work done by an ion, right? We're injecting CO2 and it forms electrolytes in the solution. The work done by the ion to establish a polarization charge in the solvent by reorienting water dipoles, we need to calculate that work done. That's the Gibbs energy of solvation. Okay, so just to recall Coulombs law, so recall that if you have a test charge Q and a single point charge little q at rest r meters away, you can compute the force that's acting on the test charge by the point charge. This is called Coulombs law. And of course, Coulombs law has this coefficient in front of it. This is the relative permittivity and the permittivity of free space. If you multiply those two permittivities together, you get absolute permittivity. So this is the, from Coulombs law, we can compute an electric potential phi, which is a function of the distance between the point charge and the test charge, okay? And this gives us a voltage. And we can compute the potential if we have Z electrons that's being contributed by a particular ion, okay? So this gives us the field strength of each charged ion in the solution. Okay, so what we want to model is we want to model the energy U that's stored in the electric field, which is the water medium, from the successive introduction of point charges. okay, in the medium. So the pink box represents a solvent, and the point charges Q are charged ions. So it's modeling CO2 injection in the water, but like I said, it deprotonates and forms charged ions. So we're introducing those charged ions into a solvent. We want to compute the energy that's being stored as we solvate those ions in the solution. So we can model this by successively introducing charges into the medium. So you start out first with a medium with 0 energy. You introduce a charge. There's not going to be any energy if you have a single point charge because of no Coulomb force, right? You introduce a second charged ion at a given distance, and you can compute the Coulomb interaction force. You introduce Q3, a third ion, and you have to consider the force acted by Q3 on Q1 and Q3 on Q2, right? You introduce the fourth charge, and you have to multiply that charge by all the other charges that are in solution. And so, yes, sir.
So are you assuming there are no positive ions that permeate field lines in this solution? In other words, there's just a much higher concentration.
Well, the sign will change. If you have a positive charge, the sign on Q will
Right,
change.
but you're talking about the energy of interacting ions at certain units.
Right, we want to calculate what is the energy being stored in the solution by introducing charged ions, right?
Mhm.
So there could be a sign on a charge. Okay, so in other words, if you have a hole, is that what you're saying?
Well, a whole or just.
Yeah,
positive-
so
yeah,
the
negative ions.
sign will change, right?
I mean, you're saying it's positive ions, in other words, protons are diffusing out much more rapidly.
Yeah, so the force is repulsive if you have the same sign and attractive if they're different.
Right.
So yeah, so the sign of the charge is considered in the calculation.
Right, but if you have positive and negative charges, I mean, there's energy stored in the attraction between them.
Right.
But they don't.
The sign of force will be different, right? Right.
But it terminates the electric field, so if you have another charge that's negative elsewhere, it's not gonna feel it, of course. I mean, maybe
Something you're missing. So we're deriving an expression for the energy being stored in the electric field by introducing successive charges, right?
Right.
So you're saying if there's a positively charged ion, a cation,
Right,
so the sign will be different on the charge, right?
yeah,
Okay. All right. So anyways, we construct this expression for internal energy, and you get this expression over here. Now we have to divide by 2 because if we use this expression, we're considering Coulomb force between Qi and Qj and Qi twice, so we divide by 2 to eliminate that. Okay, so we can arrive at a given general expression if we change the notation, the potential to VE of R, right, a function of the distance. We'll arrive at this expression right here. Now, from this expression, in terms of the potential, we can substitute in rho, which is charge density. So it's the amount of charge per unit volume, okay? So we'll introduce rho right here, okay? And once we have rho, then we can use Gauss's law, right? Here's Gauss's law right here. And so we can substitute for rho the divergence of the electric field, and then we have this absolute permittivity term that carries out. Now, once we have this expression, we can use the divergence theorem, right? Because here we have divergence of the electric field, and then we can express that in terms of the divergence of V times Z minus E times grad V. And using the divergence theorem, we can change this to a surface integral. Make sense so far? So we we recover this and we change this term to a surface integral. Okay, so here we have the expression again. Here's our surface integral. Now we make the following observation. Here at this term right here, you don't see my cursor, okay. So this term right here, we have the gradient of our potential. Now, you can use what's called the gradient theorem or the fundamental theorem of calculus for line integrals. And you can resolve that grad V term in the volume integral by using this expression right here. Okay. So the gradient of your potential is actually negative of the electric field. Okay, that's first fundamental theorem of calculus for line integrals. Now, this term, now the surface term, if we do a little analysis, we have an S, we have a V, and an E term, right? In the surface integral, we have S, the surface, V, and E. Now, S is the surface of a sphere, and that's 4 pi r squared. So this tends to r squared as r gets very big, right? E, our electric field, tends to 1 over r squared. So we have a 1 over, as r gets very big, this r squared dominates there. V, our potential, tends to 1 over r. So if we multiply S, E, and V together, right, the r squares canceled, and we have a 1 over r. So this surface integral tends to 0 as r goes to infinity. So we can drop the surface term. We can set this to 0. Okay, after we do that, then what we recover is this expression up here where we have the electric fields, squared. And that's going to give us this expression in the green box. Okay, so we have this expression, the electric field, the E dot E, okay? And what we can do is we can resolve this negative gradient of the phi term. So what I did is I did the arithmetic. Here's the gradient operator. I apply it. I calculate the partial derivatives here. Okay, and this is r squared, right? This is an r squared term to the power 3 over 2. So this approximates to this term, r over r cubed. Okay, now we'll get to this expression right here. And what I'm going to do is I'm going to substitute for your differential area, r squared sine theta d phi. Okay, and if we integrate this, we'll get a 4 pi term. Here's the 1 over r squared, and if we resolve this and do the integration, we'll come to this very nice expression right here. So Z is the number of electrons. Here's the electron charge. And then here we have this 8 pi term, which comes because we have a 4 pi from integrating this, and we had the 16 pi from before. So that's what contributes to that coefficient. Okay, so that coefficient can be pulled out. It's called the Coulomb coefficient. Coulomb coefficient. It's the 4 pi term. Okay, so we have an expression for U, which is the energy stored in the cube, which represents a solvent. So that gives us a general expression for electrostatic energy. We have the Coulomb constant shown in the green box. And what we've done is we've derived in the yellow box an expression called the Born model. So this is the free energy change due to solvation of an ion in the solution. And so this gives us this expression here for the Gibbs free energy of solvation. Okay. Now, this gives us delta G, right? And we've expressed it here. So in order to calculate this in our code, we have to have a model for the permittivity in water. And we also use this term from Helgeson to model the radius, the ion radius, okay? And it's a function of temperature and pressure. This is called the G function, the Solvation function, which I'll show you in a second. All right, so we have an expression for the Gibbs energy of solvation. We're going to use that model to compute enthalpy and entropy, because once we have enthalpy, we can calculate temperature. Okay, so in order to calculate that, we need to have an expression for permittivity. So what I used the model from Johnson and Norton, and it's a power series model, and it's the expression for permittivity of water. And if you plot this as a function of temperature, you can see that permittivity of the medium decreases with temperature. And why is that? Well, it's because that at high temperature, there's a lot of agitation of the water molecules, and they're not as amenable to reorient in the dipole. So it's low permittivity at high temperature because you can't store energy through reorientation of dipoles. In other words, its capacitance is less. Its ability to store energy through dipole reorientation is reduced because at high temperature you have a lot of agitation. Okay, so we have expression for G, and we know that G is enthalpy minus temperature times entropy. And so we have this expression. Now, if we expand it, now in the green box, we have this, the green box isn't coming. So there's a green shade right here. We have an expression, partial permittivity, partial temperature. And you can see that when this term is less than 0, you can have a situation where the entropy of solvation decreases. So you have more order. And that's because as you reorient the dipoles around an ion, the entropy actually decreases, okay? Another thing is you have this 1 over permittivity, this reciprocal permittivity in the enthalpy expression. And this is less than 1, and so this becomes negative. And so your enthalpy of solvation is less than 0 sometimes, right? And that results in an exothermic reaction. So that would cause heating of the formation water. Okay, so these are the differentials that you can compute, and there's the model for permittivity using the polynomials. We can construct these differential terms, and we have our G solvent function, which I'll show you in a second, which is a function of temperature and pressure. So this is the G solvent function by Schock and Helgeson. And this allows us to compute the rest of the terms needed for enthalpy and entropy. So this is the core of the model. This gives us heat capacity and enthalpy, and we need that to compute the change in temperature. So these are the key expressions that we calculate in the code. Okay, so once we have that done, then we can compute the source term on this advective diffusion thermal transport model, which is what the code calculates. So it's a canonical expression for advection and diffusion of temperature, right? But we have this source term S of T. So the source term, which is volumetric heat generation, has this enthalpy term, right? This is H, and that's what we compute using the HKF model that I just explained. So this term gets computed, and this is going to give us the volumetric heat generation as a result of ion-ion interaction in the formation water. That's the key. So here is the volumetric, here's the source term that I use. So this term is the change in concentration of every solute. And I showed you a table at the beginning of all the solutes, like hydronium, bicarbonate, carbonate, sodium, chlorine, all those solutes. So it's a summation of the change in concentration of all solutes times its enthalpy gives you the amount of energy that's generated as all those ions are interacting, right? So this gives you an energy per volume time, energy generation rate. Okay. All right, so that's how we compute temperature. Now we compute other things, of course. We have a poroelastic model and we have a mass transport model. And we used a finite element method formulation. Okay, it's a weak formulation. So this is the expressions we use. We compute mass transport, heat transport, and energy conservation using this model. Okay, so we use an FEM approach. And here's our porous media flow model. We use a Darcy law, and we couple that with a fluid conservation equation. We also have a poroelastic model where we compute rock displacement. So as we do the injection, we compute stress and strain on the rock and the displacement that the rock does as a result of forces acting on the solid phase. And then we finally have an equation of state. This governs density as a function of pressure. And we have a porosity model where we change the porosity of the rock using this model. So all these equations are coupled with a mass transport model, same advective diffusion model that we use for temperature, we use for mass, but the source term is, of course, mineral dissolution and precipitation. Okay, so those are all the equations that we solve and couple in the code. To set up a simulation, you have to define what the mineral composition is. So we have two layers in our simulation. We have a shale layer, which is a low permeability rock, right, to contain the CO2 you're injecting. And then we have a more porous rock, which is sandstone. And you inject into the sandstone. Okay, so these are the configurations. And as you saw on the mass transport model, our source term is a kinetic mechanism. So coupled with the transport, we also solve these reaction terms. So we have a system of ordinary differential equations that we solve, which govern the dissolution or precipitation of every mineral at the same time, right? So that's the reaction part. Okay, and then we have to configure the initial chemistry. So this is accurate to the Frio formation. This is the initial solute concentration. So we compute all these solutes in the HCAD model. These are the initial concentrations we use. And this is the configuration of the CO2 rich injectant water that we're injecting into the formation. Okay, so you can see it has we vary the molarity of the CO2 to simulate different cases, but it has much greater CO2 than in the formation itself, right? This is a very small molarity. Okay, so that's how we model it. Okay, so here, let's see. So here is plot from ParaView. It's a 3D record. So here's our code is 3D. So here is the Frio simulation. So we have a slab. Okay, it's 500 meters by 500 meters, and then we have a small perforation region. So the injection wellbore is right here in the center. Okay, and we have a Neumann boundary condition here. We have zero flux temperature on this wall, and then we have Dirichlet conditions on the side walls. And this is a very far field simulation. So the CO2 plume is contained within a small area. So we have a very large area so that we don't have, we try to minimize the effects of putting these irritating conditions on the far field, right? That's the purpose of that. Avoid, right, we have a far field. And we use different mesh size configurations. So these are X and Y cells, and then the number of cells you have along the Z-axis. So we ran several different models with several different resolutions. And here you can see a plot of the mesh. So these are all parallel pipets that we solve. And in our code, we have automatic mesh refinement enabled so that the cells that are experiencing the greatest reaction will decompose into smaller cells, right? Or cells that are very far away will coalesce. Okay, so mesh refinement is enabled. Okay, so here are some plots. Here you see on the left, you see the temperature profile on our 40 by 40 by 64 grid cell. And on the right, you see the volumetric energy generation rate, that source term that has the HKF model built into it, right? The enthalpy calculated with the HKF term. Okay, so this source term, right, is included in the calculation of temperature. Okay, so let's go to the next slide. Okay, so in this slide, in this simulation, this was on my initial slide that I showed you. This is a higher resolution a contour profile of pH. So if I keep running this, you can see over the 30-day period, this acidic front formed and developed ahead of this bicarbonate bolt front. The simulations show the same effect that was shown. So this is a latest simulation I ran. It's on the 200 by 200 mesh. And this simulation took 58 hours to run on 16 processes using MPI on a machine that has the Cascade Lake microarchitecture. Okay, now showing that the results agree with what was seen from the real data at the early slides. Here is a slice. Here is a plot of temperature at the observation well. Okay, so if you pick a point at the observation well and you plot temperature versus time at that point, this is what the simulation showed, and this is the real data, right? So this is at coordinate, this is 20 meters away at 250 meters down, and this is with 91 tons. And you can see just from this plot, the temperature decreases very sharply and then increases again. You see that? So you see a sharp decrease and then a sudden increase. And this correlates very well with this drop in temperature. Okay, so this plot over here is at 20 meters away from the injection, and this is at 30 meters away. So this is a point measurement of temperature versus time. And at 30 meters away, where the observation well was, you can see this sharp drop and sharp increase right when that acidic front reaches the observation well. So you can see that the profile agrees with the real experiment. Okay, so in this simulation, we see a lower temperature region, right, develop within the acidic region ahead of the bulk. And I'm going to call this region the diffusion front, because it's the front that forms as a result of a greater diffusivity of hydronium ion, which comes again from the deprotonation of carbonic acid. And here is another plot. This is at injecting at 3 kilograms a second, which is the same rate of injection as the Frio pilot. And you can see that there's a drop in temperature followed by a sudden increase. And again, that is at this, I don't know if you can see it, but there's a little pink point right here. So it's a single point that, and we're tracking the temperature. This is done in pair view. You track the temperature at that point during the injection, and that's the profile you get. So it agrees pretty well with what we saw from the raw data. Now, one of the problems that's caused by an advancing acidic front is the dissolution of carbonate mineral, because the whole goal of carbon sequestration is to store the CO2 in solid mineral form. So if you're injecting CO2 and you have this acidic front that forms the head of the injectant, it's going to dissolve already solid phase carbonate mineral. So that counters the whole goal of carbon sequestration, right? That's something you don't want to do. So that's a problem caused by CO2 sequestration. So what can you do? Well, what you can do is, well, just from this plot, okay? So we see we have CO2 solvation, we have CO2 gas going into aqueous phase, and then we have CO2 aqueous and water mixing to form carbonic acid, all right? And then the carbonic acid deprotonates to form bicarbonate. This marks the bulk, right, that we talked about. And you have these other reactions, right? We have autohydrolysis. Well, what's happening is, if you consider Le Chatelier's principle, if you increase CO2 gas, then reactions 1 and 2 shift to the right. So stored solid carbon in the calcite dissolves, right? That acidic front hits. You have solid phase calcite. You've stored this carbon, which is what you want. But as soon as the acidic front hits, this shifts to the right, and you'll form bicarbonate again. This is what you want to prevent from happening. Well, if you decrease CO2 gas, then both reactions shift to the left, and calcite precipitates, which is what you want. So the question becomes, how do you counteract this effect if you have this acidic front that's forming ahead and dissolving already stored carbon and calcite? Well, one thing you can do, or one idea you can do, is you can introduce what's called excess alkalinity. So along with your injectant of CO2, if you introduce a source of alkalinity, shown here by hydroxide ion, then you can counteract this, right? So then you have this other alkaline term which allows you to precipitate calcite. Now, in order to do that, you have to introduce a source of hardness. So what we mean by hardness is other ions, alkaline earth ions, that can combine with carbonate to form either dolomite or calcite. Okay, so how can we model this? Okay, so what I'm going to show you a final plot. So what I did is in this simulation, I striated injections of CO2, Okay, so we have from 0 to 100 days, we're injecting CO2. And then we have 1 day to allow the reservoir to equilibrate. And then from another 100 days, I inject a source of excess alkalinity, or a highly alkaline water called alka. Okay, now what you can observe is in the period of time where we're injecting the highly alkaline water, we see greater rate of precipitation of calcite. So what you're seeing here colored is calcite fraction, volume fraction of the reservoir that is calcite mineral, precipitated solid phase calcite. So what I'm trying to say is that you can counteract the negative effect of the dissolution of calcite from the acidic front by introducing alkaline water, which allows more calcite to form at a greater rate. So otherwise it forms in geologic time, which is over many, many years. You can reduce this to hundreds of days and increase your calcite precipitation. Okay. So this is my last, yes, sir.
So does calcite crystals form, I assume, in the pores of the rock?
That's right.
And
They form in the pores.
so that influences the porosity and diffusion further.
It decreases porosity.
Right.
It
So
can also
makes it
decrease-
harder to inject more.
It makes it hard to inject more, and it can also decrease permeability
Right.
because you have less regions for the water to flow. Yes, so that porosity model I showed you, we vary the porosity. As calcite forms, porosity decreases. That's correct, and permeability. Yeah, that is true. Okay, so to conclude, I could say that by considering interaction of charged ions, charged electrolytes in a solution, it might explain the reason for the low temperature, highly acidic front, or it could explain the reason for a decreased temperature in the acidic front that forms the head of the bulk. It can be one reason for the explanation, and we showed how the numerical simulations pretty much reproduce the temperature profile that was observed experimentally. And then the other conclusion is, as a way to counter effect the negative effect of that diffusion front, we can introduce alkaline water along with the injectant to increase the mineralization rate of carbon-containing minerals like dolomite and calcite. And it's 4:30, so exactly on time. Any questions? Yes, sir.
Yeah, how does this affect yearly commercial or government activities on CO2 sequestration? I mean, is there a lot of CO2 sequestration being done? You know, in the continental United States?
Not in the continental United States, but there is in Norway and China, but not so much in the United States. But Norway is a leader. In China, they're making great advances because China has a lot of coal burning power plants, and they have an issue with pollution. So they're making a lot of advances in CO2 injection.
Which was the capture the CO2.
Yeah, they capture it from coal burning power plants. Yeah.
So these use oil wells, or I assume they're tapped out.
Depleted oil reservoirs.
So what sort of capacity is there compared to the rate of emission of CO2? I mean, are we like, is the possibility of sequestering CO2 like 2 orders of magnitude lower than the rate we're emitting? Or this is not really related to the technical aspects of your talk, but I'm just curious. how much promise is that?
Well, I think Norway has net zero carbon emissions now, right? They're injecting into the Sleipner Formation, right, off the coast. So they claim net zero. So they inject as much as they produce. So that's in an offshore location. This simulation was in Houston because there's a lot of depleted oil wells in Houston. And Houston has the Frio Formation, which is a huge region all the way Texas, Louisiana of sandstone, which is a very porous rock that is perfect for CO2 injection. Also, it has the Anahuac shale covering it, cap rock, to prevent release of the plume back. So there are regions where there are ideal zones for injection, but I know Norway claims to be zero net.
Yeah, but I think that without knowing all the details, there is a huge amount of empty reservoirs that could be used provided that there's no state. Right. And that's what the whole thing is to certify a particular empty reservoir that is suitable for injection.
When you showed the visualization of the grid, you mentioned why also the feed. The problem seems like a symmetric problem. Why?
Why aren't these
Why is it?
X, Y plots radially symmetric?
Oh. The simulations were not symmetric?
No, so they don't act as symmetric in radial coordinates?
Why aren't we using cylindrical coordinates, which would make more sense? Is that the question? Well, what is the reason for that? Why don't we use, well, the original code I developed, before we did FEM, we used finite volume. And when I developed that code, I was used to parallel piped grids. So I would, I calculated the flux on each boundary, and I never went to cylindrical or spherical coordinate system, but that is that would be a good next step.
Your front is expanding in area by
Yeah.
squared.
Yeah.
Nice.
Yes. Yeah. It's a good point. We should move to a cylindrical coordinate system, right? Yeah.
My question has more to do with the results. I mean, if you looked at like the contour profile, the pH, front, so on and so forth, they weren't radially symmetric.
Let's see, like this plot, right? Like this one right here.
Yeah, is the stone not isometric, or what is going on?
Well, we do have AMR enabled. So the initial grid cell volume, which is initially uniform, is not uniform as the simulation runs. So it's like are you seeing like these strange effects that you're seeing? Like it's not perfectly symmetric.
Yeah, I mean, I would, if this
Yeah.
rock was, if this rock were uniform, you'd expect these profiles to be radially
Perfectly
Yeah, but
symmetric.
it's not. The rocks are
They have different permeabilities in different
It
directions.
doesn't matter what it is, the model that's homogeneous here. So
Yeah, the model is something, right.
Oh,
you're not
Yeah.
asking what is in reality, you're asking what the simulation.
Yeah, there is, you are correct. It's not exactly symmetric. If we keep running it. Well,
And just physically, if the medium is, what's the, yeah, homogeneous versus oriented. If it's homogeneous, you expect radial symmetry. It's not, you would see.
there's slight differences if you look at these contour plots.
Yeah, if you have irregular measure, under the zone in places, then you'll have a slight deviation.
Probably that's what's happening.
Probably.
So that's a good point, yeah.
that bad.
If you keep running it, yeah, it's,
The normally 10 per sticker and go out of here.